Good morning. Welcome to the session. Our second session, right? And start with look at what mutually exclusive events are. Mutually events. Bear with me, there is some noise from the background, but just need this video. All right. So when I events are said to be mutually exclusive if they cannot occur at the same time. Okay, they cannot happen at the same time. So such events are said to be mutually exclusive. All right, that's what we are saying. So we are saying events are said to be mutually exclusive if they can not occur or happen or indeed take place at the same time. Such events are mutually exclusive, right? In other words, the intersection set is empty. Okay. Okay. That's what we are saying. For example, if you toss a coin, okay, there are two possible outcomes. It's either the head or the tail turn up. You can never have a situation whereby both the head and the tail are turning up. In that case, the head and tail are mutually exclusive events. They cannot happen at the same time. All right? Okay. Maybe I can put some facts. The collection of events, let's say A1, A2, up to AA. This collection is said to be mutually exclusive if every pair of the collection, or every pair in the collection, is mutually exclusive. So what we mean is, if you have got S to the sample, then we have got these events A1, A2, A3, A4, up to AN, right? S is mutually exclusive. So if this collection is mutually exclusive if, for example, A1 and A2 are mutually exclusive. All right? Maybe A1 and A3 are mutually etc. Right? So a collection itself is mutually exclusive if every pair is mutually exclusive. Okay? Now we can look at example 1.9 in this book. example 1.9, which is here. So we are saying if we toss a coin twice, toss a coin by a tree diagram, we are going to have head, tail, or if you want, this is 1 and this is 0. Then you have head, tail, head, and when you map, possible outcomes are head, 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 tail, tail, head, and tail, tail. That's what we have when you toss it twice. All right? When you toss it twice. And this represents the sample space, the experiment. Now, so we are saying if we refer to this experiment of a coin twice, and let A be the event that only head, at least one head occurs. We are saying A is the event that at least one head. So what do we mean? We go to where there is at least one, meaning minimum of one. Then have also it doesn't matter. So we have got HH, HT, then you have who? Please take note, this is hotel. Then you have TH, according to what we have. Okay. Then B, we are saying, and the B be the event that the second toss results in a tail, meaning that the second toss should be a tail, or should result in a tail. So here we do not have a tail. First toss is head, second toss is tail, so we can pick HT. Okay. Then the second one here, the last one, first toss is the head, and second, that means the tail rather, second toss is tail. At least there is a tail in the second HT. So these are the sets that we have. All right, these are the sets that we have. So now we are saying, if you look at A union B, what do we have? We get the elements A and B put in one set. So we have got HH, HT, TH, and TT. Doesn't matter the order, which is this, right? That is A union B. But if you want A intersection B, what do we have? We have HT, HT, HT. What else do we have? Nothing. This is what we have. Okay. But now, for A complement, you need to know that A union B in this case will represent our sample space. So our sample space, like I said earlier, is HH, HT, TH, and TT, right? So if we want to find A complement, what is A complement? A complement is S minus A. Our A complement is equal to, in set S, we remove the elements in A. So in set S, we remove HH, we're going to remove HH, HT, and TH. So we remain with the TT. I hope that is fine. That is okay. That is fine. Then if you look at A minus B, okay, the difference of A and B. So from A, we remove the elements that are B. What do we have? HT, we get rid of HT. That's all. So we have HH and TH. Doesn't matter the order. We get TH and HH. What we have. I hope that is okay. I hope that is fine. Okay, then we talk about the concept of probability. Okay, the concept of probability. All right. Concept of probability. The concept of probability. Now, we need to know that probability, in the first place, probability is all about chances. All right? All about the chances. It actually denotes the possibility of an event, or maybe of the outcome of any random event. So we are saying that's about possibility, that's about chances. Is there a chance that something can happen? Okay. Or there a possibility that an event cannot happen? Okay. So by standard definition, we are saying probability is the likelihood of an event starting, happening. Okay. So they are or even not happening. Okay, so that is probability. It actually measures the certainty of an event to happen or do not happen. And this is just the following point: that number one, if we are certain that an event will occur, then its probability for occurring is 1 or 100%. What will be if we have a bag? Okay, if we have a bag, this bag contains maybe some pens, or red pens, and 5 green pens. Okay, then we say, what is the probability that when you pick a bag, you pick a pen? The probability is 100% chance that you're going to pick a pen, but you will not miss. So they are open. All right, so there's 100% chance that you pick a pen. You're not interested in the color, but just pen. All right. Then the converse is if uh, if we are certain that an event will not happen, will not occur, then its probability of occurring is 0 or 0%. All right. For example, we give an example of pens, red pens and green pens. Then if I ask you, say, what's the probability of getting an apple from that? It can't happen because there are no apples. We are certain that it cannot happen. When we are certain that it cannot happen, the probability of that thing happening is 0. When we are sure, its probability is 1. Hence, we are saying probability ranges from 0 to 1. That can be expressed as either a ratio, by ratio we mean, and can be expressed as, number 1, as a common fraction, e.g., maybe 3/4. Okay. 2, as a decimal number, e.g., 0.75. Third one is as a percentage, e.g., 75%. So these are the ways of probability. Okay. Yeah. So now, this implies that as a formula, we are saying probability of an event is equal to number of favorable outcomes, number of favorable outcomes, number of all possible outcomes. Okay, that's what we mean. So we say number of favorable outcomes, the number of times of an event divided by the possible outcomes, which is sample space. We can do a quick example. Suppose that bag contains 3 red pens and 4 black pens. If a pen is picked at random from the bag, find probability that it is A, red, B, white, C, not black. Okay. So A, we are saying probability that it is red is equal to number of possible outcomes divided by number of favorable outcomes divided by the number of all possible outcomes. What does this give us? By favorable outcomes, we are saying if we to carry out this experiment and we picked pen which is red, then the outcome is favorable as we want it. In this case, we'll say how many red pens do we have? There are 3. What is the total number of pens? We add 3 plus 4, we get 7. But we have got that. Okay. Then B, probability that it is white. So it is clear that we do not have white pens, so the probability is 3. Probability that is not black. We only have 2 events, that is black and red. So if it is not black, then that is probability of red, right? What it means. So what's the probability of red? It is the 3/7. Oh, another way of doing it, the probability of not black is equal to 1 minus probability of black. 1, remember it is 1 minus probability of black is 4/7. So we deal with as a fraction. Common denominator is 7. You cross multiply with 7 minus 4 to be 3/7, taking us to the same thing. Okay, so that's what we mean by probability. Okay. Now, there is this point that we must note. That there are 2 important procedures by means of which we estimate the probability of an event. So we estimate the probability of an event by classical approach and frequency approach, right? Now, what do we mean by classical approach? If you look at what they are saying here, we are saying if an event can occur in 8 different ways, okay, maybe it is 5 times, like the way we deal with probability of rate. What we are talking about here, right? That the three, they are the 3. Where we are saying if an event can occur in different ways, 3 different ways, right? Out of the total number of any possible ways, which is 7, of which are equally likely, then the probability is h/n. N is the number of ways, h is the number of ways, then n is the possible number of 3/7. Okay, that is the first one, the classical approach. Then the other one is the frequency approach. So after n repetitions of an experiment, where n is right, an event is observed to occur in each of these, then the probability of an event is h/n. This is called the empirical probability of an event. Now, the meaning of frequency approach is predict how many times an event occur in a larger population. For example, if you have got want to carry out a survey in a particular area, as to how many people normally have 3 square meals a day, okay? You may do a census or get a sample. Maybe let's say this population is, whole community here, it is 10,000. 10,000. You may not interview all the 10, but sample a few. Every sample 100. Okay? Then from this 100, we discover that it's only 20 out of 100 that are able to afford 3 square meals in a day. Right? What is the probability then? Probability is 2/10 is 1/5. Okay? So you can use now this probability 1/5 to predict how many people expect afford 3 meals in it from the 10,000. And this is what we are calling the frequency approach. This frequency approach is just use estimate. They not give you the exact answer, but just an estimation. Okay? Look, if you look at an example, that if we toss a coin 1,000 times and find that it comes up heads 582 times, we estimate the probability of a head coming up, the number of times the head has come up is 532 divided by the total number of times that we have tossed this coin, which is 1,000. And when you divide this by 0.532, okay, we can use this probability, for example, to say, oh, suppose we tossed this coin 10,000 times. How many times do you expect to have a head coming up? We are going to 0.532 times 10,000. Whatever answer you find, that is the number of times that we expect. Not an expectation, it's an estimation. I hope that is okay. I hope that is fine. I hope it's audible. Some noise a bit, but so that's what they are saying, right? Now, we talk about axioms of axioms in properties. Okay? In properties. What are the properties of probability? Number one, they're saying, suppose we have a sample space S, right? We have a sample space S. And that if S is discrete, meaning that they have this S. This 1, 2, 3, 4, 5. All subsets correspond to event and context. But if S is a non-discrete, if S is non-discrete, meaning that it may take an interval, for example, maybe 1 to 5 to 7, this is non-discrete. Only special subsets called measurable sets respond to each event is A. Each event A in a class of events. We associate a real number with of A. Then P is called the probability function. So what we are saying here basically is if I got probability of an event A or probability of an event, P is the probability function. What we are saying, right? P is a probability function. P is a probability function. So now, what is the first axiom? Axiom number one. Every A in C, we are saying C is the class event. So you may have C is maybe A1, A2, A3. It is a class of events. For every A in the class, every A, example A, it must be greater or equal to what? 0. Meaning that B will be negative. It starts from going above probability is always positive. If it can't happen, it can be positive. If it cannot happen, so it must be greater or equal to number 1. Number 2, for sure or certain events is class C. If you know that it will happen, the probability of that thing happening is 1. Okay? For any number of mutually exclusive events, A1, A2, A3, so on and so forth, up to AN, class C. All right, so if we have got these events that are mutually exclusive, remember we said mutually exclusive events are events that cannot occur at the same time. So the probability union A2, union A3, union, so on and so forth, maybe up to AN. So what is it? It is just their sum. So when you talk about the union, just get their sum. So this is the same as saying a bit of A plus probability of A1 plus probability of A2 plus probability of A3 plus probability of AN. That's what we are saying. But if there are only two, let's say in particular for two mutually exclusive events, that you have got A1 only and A2, which are mutually exclusive, meaning that A intersection, A1 intersection, A2 is empty. Okay? There are only two mutually exclusive events. They're saying A1 intersection A2 is phi, empty. So it means probability of A1 union A2 is the same as just adding A1 plus probability of A2. Right? Okay, so that's what we mean here by this axiom. Okay, so take note. So if, for example, if A and B are mutually exclusive, simply means probability of A B is equal to probability of A plus C, probability of what? P. Union is the same as O, and in this case, we add probability. Okay? So we go to some theorems, some important theorems on probability. The above axioms, the ones that we've already done. Theorem number 1, 1, 1. Okay? It means first chapter. Okay? Then first theorem. So if A1 is a subset of A2, it means A1 is contained in A2. Then probability of A1 must be less or equal to probability of A2, right? And because A1 is A2, that can subtract A1 from A2. So this is the same as probability of A2 minus A1, which is equal to probability of A2 minus probability of A1. This one we must see. What is the second theorem? second theorem states that for every event A, every event A, probability rise from 2, 1. That's it. That is probabilities between 0 and 1. Now, if a set is empty, or if an event is empty, probability of picking something that is empty is 0. So probability of an empty set is the, that is, the impossible event has probability. Okay. So, for example, you have a set. Let's say set S is equal to empty. All right. Set S is equal to 5. What is the probability of getting a 2 this empty set? All right. Number 4, number 4. You know that A complement, remember we said A complement is equal to S minus A, right? Now, in terms of probability of A complement is equal to S in the total sample, and the total probability is 1 minus probability of A, what we have. Okay? Probability of complement is equal to 1 minus A. That's theorem number 4. What is theorem 5? If A, say, is equal to A1 union A2 up to AN, where A1, A2 up to AN are mutually exclusive. It means we can obtain A probability of A by just adding this. Think of A1 probability of A2 plus so on and so forth, probability of AN. If at all these are mutually exclusive events, the probability of because this A may be a bigger set, then there are these others. So the probability of this one is as good as saying, let me get the probability of element that we have. So we're saying, in particular, if A is equal to S, that is the sample space, then when you add all the events inside, the probability of all the events inside, you must get one. What do we mean? Look, we have S is equal to 1, 2, 3, 4, 5, 6, which is like A. That's what we are saying. All right. So we are going to say probability of each number, probability of 1 plus probability of 2 plus probability of 3 plus probability of 4 plus probability of 5 plus probability of 6. Answer must be 1. That's what we get. All right. So what is the probability of 1? 1 over 6. Because there are 6 possible plus 1 over 6. Everything is plus 1 over 6. Plus 1 over 6. Plus 1 over 6. Plus 1 over 6. 1, 2, 3, 5, 6. And this must be 1. So if the denominator is 6, keep 6 and add the numbers. When you add the numerators, you have 6, and this will give you 1. What we mean. Okay? Next, theorem 6. A and B are elements. Yeah, we don't mind whether they are mutually. Then probability of A and B equal to probability of A plus probability of B minus probability of A intersection B. But if they are mutually exclusive, you do not need to say A plus probability of B minus that, because this is not 0. They are mutually exclusive. If they are mutually exclusive, we are saying probability of A union B is equal to probability of A plus probability of B, because there's nothing. These are disjoint sets. But for any, that is something you find the union, you must add and subtract. Okay, that's what we are saying here. So add bit of A, bit of B, then we subtract, because there's something that is to be repeated. What we are saying is that this is A and B. So if I'm going to pick A, I've already picked the intersection. If I pick A again I'll pick the intersection. So there will be a repetition. So I must remove one of that. That is why we are removing the intersection, or there will be a repetition. Next, that's when we can extend this now to a general situation. If A1, 2, A3 are 3, right? So the bit of A1 and A2 and A3 is equal to the probability of A1, bit of A2, bit of A3, then that's like they will subtract it. So there will be 3 points of this with the code. I want to say minus A1 A2 minus A3 minus A3 A1. Then we add the intersection of all. This one must take note of that. Then they are saying generalizations to event, any event, any other. Can you do this in other events? Theorem 7. For events A and B, probability of A is the same as probability of A intersection plus probability of A intersection. Look, if we have got this, if this heading represents B complement intersection A or A intersection B, all right? Now, if I want to find A will be equal to A will be equal to A will be equal to A intersection B complement plus A intersection B. That will be A. All right? Then what is happening? So, the shaded part is the B intersection B complement. B intersection B complement error. I will have found it. But there is need of this one for us to have a complete set A, which is A intersection. That's what we are saying. So we are saying then probability of A be equal to would be equal to probability of this plus probability of that. This is what we are saying. Right? But we are saying. That's what we are saying. Okay, good. So you may need some time to go through, understand, then you let me know. problems. Theorem 8. Theorem 8. If an event A must result in the occurrence one of the mutually exclusive events A1, A2 up to AN, then probability of A will be equal to A intersection A1 plus A intersection A2 plus so on and so forth. You're just adding A intersection the first event, A intersection the second event up to and so forth. These are the theorems that you need to pass. Okay, these are the theorems that you pass. Okay, then assignment of probability. We are saying if a sample space S consists of finite number of outcomes, A1, A2 up to by theorem 5. By theorem 5. And go back here. Okay? The same probability of A is the same as probability A1 plus A2 plus so on and so forth. That is, A is the union of different events. So we are saying by this theorem, probability of A1 plus probability of A2 plus so on and so forth plus probability of AN is B1. And this where A1, A2 up to AN are elementary elements. And if you remember about elementary elements, we said these elementary elements, or you can call them simple elements. Okay? Simple elements. Okay. They are elementary elements or simple elements. And what are elementary elements or indeed events? If you remember in the first lesson, we said an event consists of a single point. So these are single points. Events consist of an event consisting of single points are called simple or elementary events. So you're saying where you have A1, A2 up to N, the elementary events that they are single events, okay, or single points. Then AI is equal to more AI. AI means it can take as many points of A as you can. Okay? Okay. So what are we saying? It follows that we can arbitrarily choose any non-negative numbers the probability of these simple events. Simple events and the elementary events are one and the same. As long as 14 is satisfied. In particular, if you assume equal probability for simple events, then probability of AK is equal to 1 over N. So what we are saying is that, suppose you have got T, S. S has got T points. Okay? Maybe 1, or let's say A, B, D. Okay? Which is like A1, A2, A3, A4. This is what we are talking about here, by this. All right? Then we are saying probability of AK. AK means N of this is equal to 1 over N. Okay? Where K is 1, 2, up to 4. So, meaning that probability of A1 k in this case may be equal to how many times do we have this a? 1 divided by how many entries we have. Therefore, what we mean, k can take the form of natural numbers from 1 all the way up to n, depending on how many entries you have. So probability of k is 1 over n, where k is equal to 1, 2, so on up to n. Okay? If A is an event made up of h such simple events, okay, we don't know how many there are h of them, then the probability of A of h over n. Okay? They're saying this is equivalent to approach like we already. Okay? Yeah. So we're saying assigning probabilities provides a mathematical model, such which must be tested by experiment in much the same manner that theories and any other science must be. All right. So what you need to understand is that if I've got a sample space, then the probability of maybe AK be 1 over n, because it is only appearing once, or they are distinct. So only appearing once. So for example, what you're saying is that if you have got a sample space, 1, 2, 3, 4, 5, 6. Probability, maybe this is 1, this is 2, 3. All right. So what you're saying is that, for example, A1 is equal to 1. A2 is equal to 2. A3 is equal to 3. A4 is equal to A5 is equal to 5. And A6 is equal to 6. Then what does it mean? Simply means S is equal to A1, A2, A3, A4, A5, A6, right? And these are elementary elements or events, because an A1 is an elementary event because it only has 1 point, which is 1. So now, probability of A1, okay, it is like probability of AK here will always be equal to how many A1s do we have here? There's only 1 divided how many entries we have. That is n. In this case, there are 6. That is what we find it. Okay. Now we can now look at the examples, see how best we can solve them utilizing the theorems that were looked at so far. We are saying a simple die is tossed once. Okay? A single die is tossed once. Um, find the probability of a 2 or 5 turning up. Okay? Find the probability of a 2 or 5 turning up. Now, one thing that you need to realize is that you need to check is 2 and 5 mutually exclusive? Not. Okay? You need to appreciate that. So, Okay, so I want to use this space. If we toss a coin, how many things do we expect to have? We expect to have 16. Either 1 will show up, 2 will show up, 3 will show up, 4 may turn up, 5 may turn up, equally 6 may turn up. And it is not possible that as it turns up, 2 and 5 will appear at the same time. Hence, note here, 2 turning up and 5 turning up represent mutually exclusive terms, because these cannot happen at the same time. And we said for mutually exclusive events, this simply means that probability of 2, 4, 5 is the same as probability of 2 and 5. And since 2 and 5 are mutually exclusive, we do not expect to have an intersection set. What does it mean? Probability of 2 union 5 is equal to probability of 2 plus probability of 5. That's what we've done. So now, this implies that probability of 2 union 5 is equal to probability of, what is the probability of 2? Probability of 2 is 1 over 6 plus probability of 5, 1 over 6. This is what we were saying even in this here. Okay, if they are different single points, then probability to be 1 over n. This case to be 1 over 6. 1 over 6. So when we add this, we have got 2 over 6. Reducing it gives us what? 1 over 3. This is the probability that we have. That is the bit that we have. I hope that is okay. Now, we want to talk about conditional probability. Okay. Conditional probability. Now, what is the conditional probability? By definition, this is the likelihood of an event or indeed outcome occurring based on the occurrence of the previous event or outcome. So a conditional probability is simply the chance of an event happening in an event that something has happened. Okay, all right. That's probability. That is conditional probability. It is dependent on the other probabilities. We are saying is calculated by multiplying the probability of the preceding preceding event by the updated probability of the succeeding event. Or conditional event. Now, we are saying maybe let A and B be two events. All right, so I'm saying let A and B be two events, okay, such that probability of A is greater or equal to 0. Okay. So now we can look at some examples and maybe scenario. We're saying let A and B be two events such that A is greater or equal to, okay. Then conditional probability um, of given that we're saying conditional probability given that A has occurred is noted by like this. So this is it. A bit of A given, a bit of B given A. The probability of B given that A has taken place. Okay? Now, since A is known to have occurred, what can we say? It becomes a new sample space. Sample space. Okay? Replacing the original, which is S. It becomes the new sample space now. Hence, they're saying probability of A given that, probability of B given that A has occurred is equal to probability of A intersection B divided by probability of A. And according to the book, this is point 17. Just refer to it. Okay. Okay. Yeah, so we are saying this is what we have, 17. So if you work out things, probability of B given that A has occurred is the probability of A intersection B divided the probability of A. If you introduce one and multiply, we have a situation whereby we have the probability of A intersection B equal to probability of A by probability by the condition of probability. Rate of B given that A has taken place. That we have. Okay, this is what we have. Now let's look at the question. Let's look at a question, an example. Find the probability that a single toss die without a number less than 4. A, no other information is given. B, it is given that the toss resulted in an odd number. So here, we are saying let B denote a number 4, implying that this is equal to 1, 2, 3. That's what we mean. Okay. Now, we are saying this B is the union of the events. A 1, 2, 3 turning up. We see that by this theorem, probability of B will be equal to probability of the individual element. That is probability of 1 plus probability of 2 plus probability of 3. And this is 1 over 6 plus 1 over 6 plus 1 over 6. This is 3 over 6. When you reduce, you get half. All right? If we do not have that information, then for B, we need to find the probability of a die, which will result in a number less than 6. If it is given that the toss resulted in an odd number, toss resulted in an odd number. When they say that let be a number that is less than 4, then we can say A and odd. All right. Now, from 1, 2, 3, 4, 5, 6. Which ones are our odd numbers? Okay. Odd numbers are numbers that are not divisible by 2 exactly, or once divided by 2, you get a remainder. So we have got 1, 3, and 5. Okay. That's what we are saying. So now, we want to find the probability that we get a number that is less than 4, given that number, given that both resulted in an odd number. We want to find the probability of B. B is a number that is less than 4, given that the two resulted in an odd number, which is A. I hope that the question is clear. And we say the probability of A intersection B divided by probability of A. Now, probability of intersection B, we are saying we want numbers that are odd and are also less than 4. So we have got 1 and 1. So that is 1 over 6, right? Take note, maybe do that. We have got 1 here and 1, 1. Then you have got 3 and 3. So we have got 2 numbers. We have got 2 numbers that are common. 2 of them that are odd and less than 3. We have got 2 divided by 6. Then this is divided by A, probability of A. And what is our A? Our A is an odd number, right? And how many odd numbers do we have? How many numbers do we have? How many odd numbers do we have? How many odd numbers do we have? Here there is 1. So there are 3. We have got 3 divided by 6. So what do we have? Probability of B given A is equal to when you reduce, you have got 1 over 3 divided by 1 over 2. This is the same as 1 over 3 times 2 over 1. And this is 2 over 3. This is what we have. Okay. I think that's why we end the presentation. This is our second presentation. How I wish for the third one, we can do a live one so that we interact with our questions. Right. Till next time. This has been Mr. Phiri. Okay. Bye-bye.